Hello there. I'm Professor Marcos Santos, and today I'm going to talk about so important definition, so important idea of the operational research. And I start with a question. What is a model? We need to understand what is a model to be able to work with operational research, because in operational research, we work all the time with models, mainly analytical models. So let's see a short presentation. So far, so good. Yeah. This is the question. What is a model? So here we can see a model, an analytical model. And in the context of operational research, we will work with models all the time, like I said. So I need to know exactly what means this word model in the context of the operational research. And I start with this joke, like ironic, like this sentence was spoke by George P. Box, and he said, all models are wrong, but some are useful. What did he mean? What did he mean? I don't know if why all models are wrong. Why? We need to understand why George Box said this sentence. So let's go. Why? First, every model is a simplification of reality, because the reality is too complex. So I need to decide about something. But I have so many things that I need to analyze to be able to decide. So it's so hard to decide with many details, many parameters. So I need, so that's why I can say every model is a simplification of reality. So I reduce the complexity of reality by removing data that doesn't contribute to decision making, or sometimes data that contribute a little bit to decision making. I can say many times we have 1,000 data, and many data contribute a little bit for my decision. So I have to choose the main data that that the main data is more important to my decision making. But take care. This data depends on the phenomenon we are studying. In a specific situation, I can have a data that it isn't important for a specific phenomenon, for example, phenomenon A. And in other specific case, the same data can be extremely important to my decision making, you know? So, for instance, I can have another problem, problem B, and the same data is not important for a problem A, but these data are extremely important for a phenomenon B. So you need to analyze the problem and the data that you have. So let's see this situation. Let's imagine that we have a sailor. We have a sailor. And this sailor wants to navigate to Bahia de Guanabara Bay in Rio de Janeiro. For instance, he can take a picture, he can take a photograph, and, oh, okay, here I have a Bahia de Guanabara Bay photograph. And I can use this photograph to come in Bahia de Guanabara Bay. But look, if you think for the sailor, this picture, this photograph is so confusing, because he has so many data, so many information. And in this photograph, we have mountains, we have beach here, lakes, and buildings, another lake. Clouds, islands here. So in this photograph, we have so many data that they aren't important to this to decision making. To these data are not important for the sailor. You know, you understand? So from this photograph, I can draw another picture, more simple. I can draw another picture like that. I can draw another picture, more simple than the first one. And in this picture, I will draw only the most important data. for decision maker of the sailor. So I need the coastline. Okay. It's very important because the sailor will navigate here and he can come in inside the Bahia de Guanabara Bay. You know? What else? Look that in this picture, you don't have mountains because these mountains, they aren't important for the sailor. You don't have clouds and you don't have houses here, buildings. You don't have many things that they aren't important for the navigation, you know? So here, the first one, I can consider more or less, but I can consider here we have the reality, but reality is too complex. So I can simplify the reality and I can make a model. And in a model, I will put only the main data that I need to my decision making, you know? So this is the meaning of a model. That's why George Box said our models are wrong, because in a model, I don't have many data that I have in the reality. So if I want to be rigorous, I can consider that all models are wrong, but they are useful because it's easier to decide with a model than with the reality. So let's talk about the Newton's second law. I think everybody know that Newton's second law is F force equals mass times acceleration. I think everybody saw this expression, this equation during the college. So look, take care. I just can use this expression in a very specific situation that the mass is a constant. I don't have variation of mass in my phenomenon, you know? But in many situations, I have a variation of the mass. And I will give you an example Next, next slide, next picture. So, Isaac Newton didn't that F is equal mass times acceleration. Newton said the following expression: F is equal variation of movement quantity over the variation the time. This is the Newton's second law. So here we have F. I can say F equal variation, okay, and I can say okay, and here we have mass times movement quantity is equal mass times velocity. And here we have dm/dt times v plus m dv/dt. Yeah. So this is the expression. This is the Newton's second law. F equal dm/dt times v plus m dv/dt. Okay. In a specific situation that we have that the mass is a constant, I don't have variation of mass. Here we have 0. So this part of the equation disappears. And we have F equal to m dv/dt. And you know that dv/dt is acceleration, right? So we have F equal mass times acceleration. This is the formula, the expression that we saw in our college. F equal to mass times acceleration. But look, this expression, I can say that it is a model, because F equal m times E is a specific expression that I can use in a specific situation that I don't have variation of mass. You got it? And you can say, Professor, but in what phenomenon do I have variation of mass? I can show one example to you. Look this example. Here, I think is challenging this shuttle. I think so. Challenger or Discovery. I don't know. I think it is Challenger. So in this case, I have a huge mass here, huge mass, a huge mass of fuel that burn along the way, and more than half of the mass is fuel that will burn along the time. So in this case, I have a variation of the mass. And now I can't use F. In this case, this model F equal M times E, this model doesn't work. This model is wrong, like George Box said, because I need to take care with the phenomenon that I am analyzing, I am studying, I'm trying to understand. So I need to understand that I have a variation of mass here, and that's why I can't use this expression. So I need to use F equal dm dt times V plus M dv dt. This is the correct expression that I need to use. You got it? So, this expression is wrong in this case of the space shuttle, because here we have a huge mass of fuel that will burn along the time, you know? But in other situation that my mass doesn't change, I don't have variation of the mass, like a stone, for instance. If I take a stone, in the stone, with a stone, I don't have mass variation, for example, for instance, you know? So I think that it's not correct to say, oh, a model A is correct, a model B is wrong. This is not the case. I need to figure out if my expression can represent one specific phenomenon. That's the case, you know? I need to figure out, oh my goodness, this expression, this formula, this law, this equation here, I can represent this phenomenon with this equation, yes or no? Oh, yes, I can. So this model is good because I can use this analytic model to describe this phenomenon, you know? So I think that's the case. I need to think about the expression, the model, if there is a match between the phenomenon and the expression. I need to think if there is this match, you know? So F equal M times E, it isn't wrong. This is not the case. If my mass, if I don't have variation of mass, it's okay. For instance, a stone, a door, whatever you want that you don't have variation of mass, you can use F equal mass times E. But if you have variation of mass, you can't use F equal M times E. You see? You see where I come from? Okay. And here, for instance, we can see many models, many operational research models. In the context of the operational research, when I said a model, I mean mathematical models, you know? So every time that I say, let's analyze this model, let's see this model here in Operational Research House, I mean analytic model, I mean mathematical models. So we work with mathematical models in operational research all the time. This is our habitat. So, for instance, here we have a linear programming problem, very known methodology inside the operational research. Here, for instance, we have a problem of the breadth theory. For example, a traveling salesman problem is another problem, another analytic model. And here we have another model called COPPE. Was developed by Professor Carlos in Brazil, TOR method. And now we have TOR 1 and TOR 2. TOR 1 and TOR 2. And it is a fantastic model, fantastic mathematical model. I have used it many times with my students here in Military Institute of Engineering. And here we have a normal Cook curve, normal distribution in statistics. And like I said, we will work with mathematical models in operational research all the time. So the conclusion is, what is important that you have to learn that you have to put in your mind a model is a simplification of reality, because the reality is very complex, is very confused. So I need to make a simplification to understand better the reality. And this, I need to make this simplification with a clear goal, like I showed an example of the sailor. The sailor has a goal. He needs to navigate to entrance of the Bahia de Guanabara Bay. So he has a specific problem, the entrance of the Bahia de Guanabara Bay, a very specific problem. So I can use a model that I can solve this problem. So this is the idea that I want you need to put in your brain, put in your mind. A model is a simplification of reality with a clear goal. That's it. You know, if you think about the Bahia de Guanabara Bay and the sailor, if you think about Newton's second law, I'm sure that you will understand that the model is a simplification of reality with a clear goal. So that's it. And if you wish to contact me, these are my contacts. I am on LinkedIn. If you scan this QR code with your cell phone, you can connect me on LinkedIn. And my ResearchGate on my profile. In the ResearchGate, you can find 100 of research. I think I have more than 500 papers, published papers, international papers of the Congress, symposiums, meetings, and IEEE, and many other papers that I presented in China, USA, Ireland, and many other countries. And I think today I have more than 500 published papers. And all my papers are in my ResearchGate profile. And this is my email. And with this QR code, if you scan with your cell phone, you can connect me on LinkedIn. So that's it. I hope, okay. I hope that you enjoy this video. If you enjoy, please give me a thumbs up and subscribe in Operational Research House, my channel, and help me to grow the visibility and help me. And you can see many others videos. I recorded more than 300 classes about many different methods: simplex method, travel salesman problem, Kruskal algorithm, Monte Carlo simulation, discrete simulation, Q theory, constraint theory, theory of constraints, TOC, yeah, theory of constraints, and many other methods. There are more than 300 classes on my YouTube channel. So I hope you enjoy, and see you next time. Bye-bye.